So the big question in 2.5 is what is an antiderivative? And we're going to go work on finding these antiderivatives because that'll help us with really what chapter 3 and chapter 4 are about as far as integration is concerned. So the easiest way that I can describe an antiderivative is just that it is another function who has a derivative that we're looking for. So for example, let's say we had a function, I don't know, we'll call it f, it's a function of x, and it's equal to, oh, I don't know, let's say x squared. Now the question might be, what function has a derivative of f of x? Meaning, let's find another function, let's just call it g of x. We want to know what that guy is equal to, so that when we take the derivative of g of x, we get f of x, which is x squared. So we want to see, can we find a function that when we differentiate it, we get x squared? So essentially, really all we're doing is we're working backward. Okay, we're trying to find a function who has this guy right here for a derivative. So we might guess at it at first. There'll be techniques that we'll use, but at first we might just say, well, we know that when we take the derivative of, let's say, x to the third, so our guess might be, let's let g of x be equal to x to the third. Now let's check to see what g prime is. Okay. Well, if we differentiate this, we get g prime of x is equal to 3x squared. So that's close to x squared, it's just got this 3 out in front. So then we might say, well, okay, so this doesn't work, but we need to get rid of this 3. So what if we go back to the original and instead we say something like this? We say g of x is equal to x to the third over 3, or 1/3, or another way of looking at this is 1/3 x to the third. Now when we differentiate, we get 1/3 times 3 times x squared, right? Drop the 3 down, subtract 1 off of it. 3 times a third is 1. And there it is. We get just x squared. So g of x, if g of x is equal to x to the third over 3, then g prime is equal to x squared. So what we found, this g of x, this guy right here, that is an antiderivative of this function. Now, you might say, I'm not saying this is the antiderivative, I'm saying it is an antiderivative, meaning that there's probably more than one antiderivative. In fact, there's an infinite amount of antiderivatives. Let me show you. So one thing we have to be careful with is more than one answer is possible. For example, what if I said instead of g of x is equal to x to the third over 3, what if I let g of x be equal to x to the third over 3 plus 1? Now if you differentiate both sides, the derivative of this we already know is x squared, and the derivative of this is 0. So this is also an antiderivative. Or what about this guy right here? Well, if you differentiate that guy, again, you get x squared. So these over here are both, these are two more antiderivatives. So we have one of them here, we've got two of them here, and here's the third one. And in fact, if I just add or subtract any number I want, put a constant at the end, then I get an antiderivative. So in general, our antiderivative, we'll call g of x, that's equal to x to the third over 3 plus or minus some number. So I'll just say plus some constant, where c is an element of the real number. So if you add or subtract anything here, it doesn't change the derivative. Now let's think about why that is. If you go back and you look at, let's look at g of x. So my original g of x was x to the third over 3, just like that. Now, if you plug in one of the other ones, x to the third over 3, let's say plus 1, all it has done is shifted the entire function up. But remember, the derivative is the slope of the tangent line. So if you're here at -1, and you're either here or here, this point or this point, both of them have the same slope right here. They have the same slope for the tangent lines. And if you went over here, let's say to 1, here's the slope, here's the slope. They both have the same slopes. So all we're doing is we're raising, by adding a constant or subtracting a constant from the end, we're just raising the function up or down. Okay, so we're shifting it. Does that change the slope of the tangent line? Certainly not. Okay, so that's why all of these have derivatives that are x squared, because x squared is the slope of the tangent line, and the slope of the tangent line doesn't change by just shifting up a unit or down a unit.